Welcome in this MRC seminar. Today we are very happy to have with us Professor Shin from the University of Florida, a rising star in robotics. She did her undergraduate studies at the Seoul National University, South Korea, in naval engineering, and then she joined the Cornell University, where she did her PhD in the Department of Mechanical Engineering. And since then, she joined the University of Florida, where she is working on a number of exciting projects involving perception and planning. Today, she will speak to us about active perception in a dynamic and unknown environment. Jane.
Thank you for the introduction, Yanis. Hi everyone, nice to meet you. My name is Shin. I'm an assistant professor at the University of Florida in Mechanical and Aerospace Engineering Department. I am leading the group named Active Perception and Robot Intelligence Lab, which the acronym is APRILab. So I'll be introducing a few projects that's going on in my lab with the title of Active Perception in Dynamic and Unknown Environment. And I hope you to find some interesting collaboration ideas based on my presentation. So please ask any questions anytime, or please talk to me after the talk if there's anything interesting. So I'll start with a really broad introduction. So we now have a lot of autonomous robots in our lives and across different domains. And they are really possible because of various sensors that are on board our robots. For example, we have autonomous driving cars where we have camera, radar, or sonar sensors that can help us detecting the lane or pedestrians or signals. And in drones, we can use them to do gas leak detection in oil and gas plants. And this is really possible because we can equip the hyperspectral camera on board the drones. So we can detect specific wavelength of the light so that we can detect the gas leaks autonomously. And also, we have underwater robots, and most of the time we don't have enough light, so we can equip those side-scan sonar sensors on board our underwater robot to detect and understand what's inside the water. This kind of advancement in sensing really brought a new paradigm in sensing control and planning community. So traditionally, we've been focusing on the feedback loop that's focusing on the vehicle itself. So for example, you have an airplane and you're interested in controlling the altitude, heading angle, or angle of attack, or the speed of the vehicle. So it used to be the traditional paradigm, but with those sensors on board our robots, now we are bringing in this sensor into our feedback loop so that we can incorporate those information from the sensors that are detecting information from surrounding environment. And due to this nature of exteroceptive sensing, our sensing capability really depends on the environment. So if the environment is really not good, then our perception algorithm may fail. So the research question that I want to address is how can we overcome those limitations caused by the environment? So I'm going to introduce 3 different projects that I've worked on. First, in underwater environment. Second, about long duration operation. And third, about navigation in dim light condition. So I'll start with the underwater work. So I've been working on underwater search and rescue related tasks, focusing on underwater object recognition. So for those of you who are not very familiar with how these things work, I prepared a short video on... Sorry, no worries. So I prepared this video to kind of animate how these things work. So in underwater, we usually use autonomous underwater vehicle that is equipped with side-scan sonar like this. And it emits the pings to the sea bottom, and you stack up the reflected signals like it's shown on the upper left corner. So you're stacking up the reflected signals, which look like an image, but with the shadow pattern that is acoustically unique. So in this video, it's describing the search and rescue mission for the missing airplane. So this is a general concept of how this underwater search and survey mission works. it sounds very easy, but it's actually very challenging. And there are several reasons that's coming from the fact that we are being in underwater. So first of all, we have to rely on sonar sensors. And sonar sensors are very noisy, and it's very difficult to understand what's inside. So still, there are some human operators who are reading those kind of sonar, side-scan sonar imageries days and nights. And because we cannot get really high context like camera images, you have to detect multiple images from different views to really understand what's on the seabed. And second is that we always have communication constraints. First, you cannot have GPS, so always there's some navigational errors. And also, once you deploy your underwater vehicle, you cannot really communicate back to the host ship. So if you deploy something and then it's doing something, and if something goes wrong, you actually don't know what went wrong. So you actually waste like 3 hours underwater, and then it comes back and you realize that there was something going wrong. So usually it tends to be very time consuming. So I'm gonna explain the underwater object recognition mission that I worked on, starting from the general framework. I want to relate this with the Titan submersible search accident that we had recently. So this is the actual pattern that they used to search that missing submersible. As you can see, you have some region of interest, and then you have to do this kind of land-more path to cover the whole region that you're interested in. And you're usually doing this using low-resolution sensor that has large sensor field of view. And after that, you will need to do a re-identification. So from the pre-surveying, you get some general understanding and some objects that are of interest, and then you have to revisit to each object to really classify and understand what they are. So in this case, revisit these multiple objects are needed to identify the targets, because you might have some clutters mixed in. And also, when you are visiting the target, you're actually using a more high-resolution sensor, which has smaller sensor field of view. So it tends to be very time-consuming. And also you're using mobile robots, so you have limited battery hours. So you want it to be time optimal, and also at the same time, you want to get some satisfactory classification confidence. So really, so I want to explain more about that multi-view planning concept. So these are the images of a same object that's obtained from different angles. So if you take the image from different aspect angle, as you can see, you actually obtain different information. So what you really need to do is you need to optimally choose the best views that can help you understand what the object is. So here I'm applying the concept of planning for perception, or active perception here, to do the multi-view planning. So here the goal is to find the most informative views and plan the path to obtain them in a minimum time for satisfactory classification confidence. And to be specific, we were using Bayesian network model for inference, where we are making the model that is representing the relationship between the features that are extracted from the sonar images, the viewing angle that you're looking from, and the target class that you're classifying. So we are using probabilistic approach to get the confidence level. And here we are using information theoretic function to really quantify the information that we are getting from each view.
Is this the MRC seminar?
Yes. So I know it was not enough explanation, so I actually prepared a little cartoon to explain what's really going on inside. So usually when you have this object of interest, you usually take the first view, like I notated there, and then you obtain, let's say, that kind of side-scan sonar image. And what you do is you extract the features, and based on the Bayesian network model that you have, you do the classification. And let's say that you have that kind of probability distribution, which actually shows something like it's 55% wedge and 45% cylinder. You're not really certain about the classification. So what you do is you move on to the next waypoint, and then you will get another sonar image, may look like the second one. And then now you're getting different information from the image, and then you extract the information and you update your belief on it, and then you will have another probability on the target class. And because now you're getting different information, you are more certain that this image is a cylindrical object. So this is usually how it works. People tend to collect images and until they have certain threshold in the confidence level. But this works after you get images. Then how do you actually choose the best view before you actually obtain images? So that's where we are using planning idea here. So this is what we are doing inside. So we assume that we are going to move on to the third waypoint, and then we think about possible observation that we can get from the third waypoint. And we will have some distribution over the measurements that we can get. Some measurements are more probable to get. Some measurements will be less probable to get. And based on that, we update our belief function, and then we use that as a predictive confidence level for target classification. So really, the objective here is to minimize the path lengths while we are securing a satisfactory classification confidence. So we really need to choose the most informative set of views for a target classification. So this work was done during my PhD, last year my PhD, and we were able to collaborate with Naval Surface Warfare Center in Panama City, and they were able to do some sea tests as well. So if I summarize everything in one sentence, although we had a lot of results, really what it's saying is the information-driven planning reduces the travel time significantly, and over the test cases, we were able to reduce ranging from 11% to 51% of the operation time, while we were getting similar classification confidence level. And also we are doing tests in simulation, and after we test in the ocean, we actually were able to get similar results, which is telling us that it was actually a feasible path that can be executable from the real vehicle. So this is a happy story, and we learned a lot from here, but actually you learn more from your failure. So I wanted to share some lessons that I learned from this experience. So first experience that I want to share is that localization uncertainty grows as you navigate. So I know this sounds very obvious, but it really felt big to me because we did this hard work to reduce the travel time and classify the target. And it worked well, but there was one problem. Because we were actually making a lot of turns and we were traveling a long distance, what happens is the UUV doesn't know where they are. And what they have to do is they have to surface all the way up to the sea surface and then do the GPS correction and then go back again. And that's actually taking a lot of time. So we were reducing a lot of time by doing this. That was actually consuming all of those times. So that was the main problem that we noticed. And the second one is that we are doing this target recognition. And what we were doing was we were actually training our ATR, the target recognition algorithm, using the data that looks like on the left side. So we were assuming that there will be flat seabed with object. But in real world, you don't know that your seabed might have some sand ripples. In that case, as you can see, your algorithm cannot detect the object. So you need to be prepared for those uncertain environments in underwater. So that really led to my current research, which I'm going to introduce from now. So that's tying into the second project that I want to introduce today, which is about GPS-denied long-duration operation. So I want to do a broader introduction on that long-duration operation. So there are a lot of challenges in those missions. First, GPS is usually not available or easily get jammed. Underwater, of course, you don't have GPS, but if you fly over the sea or the forest, you can actually get your GPS jammed. And if you actually search on Amazon, you can find the GPS jammer that you can buy. So it's really easy to get jammed. Second is that maybe you can try some visual-based method for localization, but they are weather dependent, as you can see on the right side. And third, those vision-based methods are not very robust in repeated features. So if you actually fly for a long time, you might see those kind of sea, which is repeated pattern, or the forest that has a repeated pattern. Underwater as well, you will have repeated patterns in the seabed. So how can you overcome this kind of limitation? And one thing that we wanted to try was using Earth magnetic anomaly map. So this magnetic field map is generated by the Earth crust. And the good thing about it is actually available globally. And second, it is robust to the weather conditions. And also, it's not very easy to be corrupted. So magnetic field intensity decays at a rate of 1 over r cubed, where r is a distance. So even though you have some objects, it's really hard to corrupt your signals. So we decided to use this magnetic field map for localization in long duration operation. So now the question is, how can you utilize the magnetometers for this long duration GPS denied navigation? So here I'm applying the same concept of planning for sensing in magnetic navigation. So we want to utilize this pre-known Earth magnetic field map for localization. And moreover, we want to actually take some advantage of the fact that we know the map in advance. So we want to utilize the gradients on the map to reduce the localization uncertainty. I can explain a little bit more with the figure on the bottom. So let's say that you have to move from the star to the cross marker. And if you take the yellow path, because you're getting very similar signals from the magnetometer, you actually don't know where you're at specifically. So you might have high localization uncertainty. But if you actually take the red route, you will actually go through some gradient and you will be able to see the changes in your magnetometer, which will help you to localize yourself. So that's the idea that we wanted to use for magnetic navigation here. So we introduced the similar approach of using expected entropy reduction in localization into planning. So what we really did was to consider possible actions at a given point, like you're seeing on the white arrows, and then you sample some expected measurement that you will get if you take each action. And based on those measurement distribution, you can do the same thing. You can expect or you can predict the future localization probability distribution, and then you choose the one that can reduce your localization uncertainty the most. So that's what we did in this work. And here we actually have to consider multiple objectives. One is for localization, and second is to reach to the goal as soon as possible. So we tried with this weighted function as our first approach, where we have uncertainty reduction term and time optimality term, which is basically the distance towards the goal, to consider two different objectives at the same time. Okay. And then we actually wanted to test it out. So we got to this set up in our indoor lab. So what we did was we have this magnetometer on board our turtle boat. We have vector and scalar magnetometers, because if you have your own robot and if your robot moves, because you move, you change your magnetic field around you. So you have to do on-ship calibration. And this on-ship calibration can be done by this Toll-Lawson calibration, which is a really well-known physics-based calibration method. And to do that, we need XYZ value and also intensity. So we did this calibration and we got this result where red is the value that you got. The blue is a true value and the green is the estimated value. So because green and blue are quite similar, we were able to tell that it's quite good ability of on-ship calibration, so we just use this calibration method. And then we actually obtained the map of our indoor map. And we actually print it out and attached to the bottom for visualization purpose. What we did was we obtained the magnetometer measurement at every foot, and then we integrated into that map. So it looks like this, and that corresponds to the paper map that's attached to the bottom of the floor in our indoor map. There are three things that I want to point out. First, this map is inside our indoor limited space, but it's actually representing the Earth magnetic field map on the Earth. So we're actually doing some experiments thinking that it's the Earth, like a large scale map that we're navigating. Second one is that we actually were able to get those features in our indoor lab because of other structures of this indoor building. For example, because you have pipes going under your floor, we have some giant equipment on the lower floor. So that's actually making unique gradients of our magnetic field map. So that's why we were able to get this kind of features in our map. Third, we obtained this map once, and then we obtained this map again 3 months later. And then it actually didn't change much. So it is actually reliable for us to test it indoor. So we decided to use this map to test our idea. So I want to show you the 2 videos where first, we don't care about the information about the localization uncertainty. And second is when we consider that value. So again, we are starting from that position, looking onto the left side, and then this robot has to go to the X marker as soon as possible. And this is what happens when you don't consider the localization uncertainty. So the turtle boat makes the sharpest turn that it can make so that it can reach to the X position as soon as possible. And on the bottom side, what you see is a particle filter estimation, and you can see that you have really large covariance here. So first graph is a localization error, second graph is the entropy on position estimation, and third one is a covariance from the particle filter. And then we ran the same experiment by actually putting the information gain function inside our cost function. So if you actually put that inside your planner, what happens is it's not making the sharpest turn that it can make, but it's actually detouring to that gradient region so that it can reduce the localization uncertainty. So that's what you're seeing on the lower figure. You actually have less covariance on your localization. And that is also shown in this graph too. So what we really learned here is that with the information gain in the cost function, the vehicle is guided to pass through the peaks where it can reduce the localization error. And by passing through the peak, the localization error or localization uncertainty really is reduced, and it's kept low. And it's shown in the graph right there. So this was the first work that we did. And then based on this observation, we actually wanted to move forward. So this is the observation that we got. What we realized is we can localize our robot because of the gradient of our field, which means the spatial frequency of the map is the thing that's giving information on our localization. So we wanted to really characterize this information gain more mathematically. So as you can see, we actually ran 4 different paths from left to right, and the circles are showing the covariance of the localization. And I made a box over the time when your localization uncertainty reduced a lot. And it is usually when you're passing through the gradient of the magnetic field map. So the question here is that how can we formulate this uncertainty reduction in terms of spatial frequency in magnetic navigation? And can we actually extend this into global planning? So previously what we did was we were choosing the best next action or best next point to navigate, but can you actually do it more globally? So we applied this concept of entropy map, which is using a sliding window. So what we are doing is this. So let's compare the red box and the yellow box. The red box has more features, and the yellow box has less features. And we're computing the entropy of that box to really represent the spatial frequency of that point. So what we did was we compute the entropy value of a certain window centered at each position, and then we did the sliding window concept to compute all the values over every pixel. And then the location with the low entropy correlates to the areas with a high spatial variation. And then we obtain that entropy map that you can see on the most right side. And then we apply the potential navigation method, potential field method, to combine with the time optimality and the localization information gain. And it looks like this. So we are starting from the red star to, yellow star to red cross marker, and you can actually use that potential field to find the shortest path from star to the cross marker. So here is the comparison from the hardware experiments. One thing that we noticed is that the red line and the blue lines are from the previous method, which was the local planning. And the difference here is that previously we started the robot by looking into the left side, but this time we were actually looking onto the north direction. And the result or the performance really depends on the initial condition that you start if you're taking the local planning method. But if you take the global planning method, no matter which initial condition that you have, you can actually find the best path that can reduce the localization error and at the same time finding the shortest path by weighting functions. So moving forward, there are still unsolved questions about this magnetic-based navigation. First is on anomaly detection. So in underwater, there can be something that we didn't know about. So you might actually measure something from magnetometer that is different from your map. What you need to do is you need to really distinguish whether that signal is coming from something unknown or is it just an error from your map. So you need to really distinguish those two while you're navigating. And also, this is a picture of existing magnetic field map. And you can see that there are some empty spots because you actually couldn't sweep everything. What if your map is partial? What can you do? Can you build a map while you're navigating? So that's the problem that we are looking into. And also we are thinking of a multi-agent system where we can intentionally coordinate multi-agent system and then move together. And based on that formation, we can compare the magnetometer sensor readings. And based on that, we can do anomaly detection, or the value differences can help us for localization. And then coming back to the second lesson that I presented. As I said, your images can be the upper one or the lower one, depending on the environment that you're going to deploy your vehicle. And you never know before you deploy. So how can we address this kind of problem? And one idea that I was thinking was about fusing different sensing modalities. So this graph on the left side, the red line is the magnetometer sensor reading. And they have the first peak when it's passing through a mooring block, and they have the second peak when they're moving over the mooring chain. So based on these signals, you can actually give some context for your object recognition so that it can be prepared or it can react to those uncertain environment or unexpected environmental conditions for your detection algorithm. And as a preliminary work, I've been working on fusing different sensors. And specifically, I was looking into IR image and RGB image fusion and focusing not on the early stage fusion, but later stage fusion. And the reason of using those later stage fusion was to really get some explanation, the ability to explain things. So we were actually using Jaejeong network to fuse the information from each modality. But because we were only using the detection decisions, we actually are throwing a bunch of context from the raw signals. So we are searching for a good method that can meet somewhere in the middle so that we can be efficient in terms of fusion, and also we can get enough context for the fusion too. And also we're looking into some cyber and physical attack environment where one modality can get attacked from other people. In that case, we are trying to come up with a fusion method that can maintain the robustness while the attacks are present. So that was the second project that I wanted to introduce. And now I'm moving on to the third project. So third project is about navigation in dim light condition. So when I heard dim light condition, I'm usually thinking about this kind of picture. You have to fly or you have to navigate in this dark night. How can you effectively and efficiently do perception for navigation in this dim light condition? And we wanted to actually learn this efficient night vision system from nocturnal insects. So the question that we had was, how do their eye structures affect this effective or efficient information extraction in dim light environments? And what is their unique advantage in planning and control? So we wanted to learn from insect vision system. I'm collaborating with Dr. Jaejeong, currently in Georgia Tech, and I wanted to show some videos from his slides. So actually most are nocturnal insect who can fly really well in dark nights. And this is how they find flowers in really dark night. So even though you cannot see very well, you can still find the flower, the nectar, and it can fly very well. So we decided to look into their structure. They have superposition compound eyes, and they have large facet lenses. They have wider rhabdomes, and they have reflecting tapetum. So that on the right side is the structure schematic of the moth eye. And what really happens is you have multiple lenses in one eye. And one ray can go into different lenses. So you're actually getting more information in dim light condition. So this is a CT scan, from micro CT scan of moth eyes. And that eye is actually almost 1 millimeter, but you can still get the structure of it. And this is a CT scan video, which is allowing you to really learn the internal and external structure of the moth eyes. So we really wanted to adopt its structure into the perception system in dim light condition. And as an engineer, we started with a simulation. So we did some preliminary experiments with simulation, and I wanted to share some preliminary results with you today. So to do the simulation, we were using an open source, high-speed and high-fidelity rendering simulation called compound rays, and we were able to get some data. So this is a scene that we made in Blender, and we were able to render what actually moth sees, and this is what we got. So they are the same images, but the only difference is about the resolution. So it takes more time to obtain the right image because it's getting more rays and then it's more smoother. But still, you're actually getting similar images. So this image is actually obtained from the camera located over there. I don't know whether you can see, but the black part is where the camera is located at. And this is what actually moth sees. So what we wanted to test first is a yaw angle estimation capability. So what we did was we planned this cylinder to make some background for optical flow. And then we were assuming that the camera is only moving on a plane with only the yaw motion. And then we wanted to estimate the yaw angle of our own camera. So really, the camera was located in that white dot, and then it was looking like this, and then it's rotating with only the yaw angle. And we wanted to estimate the yaw angle of the camera. If you render this using just camera, then it looks like on the left side. And if you render this using this compound ray, which is really doing the compound eye structure rendering, it looks like on the right side. There are many differences between those two eyes. What if we apply the optical flow here? So this is the results that we got from optical flow for camera rendering and compound ray rendering. There is a big difference. Can you guess? Yes.
On the compound ray rendering, when you apply optical flow, you can see the outlines of the objects better.
Yeah. So what really the difference is, the camera rendering estimates the movement from the features from the wall. So it actually detects the features moving on the wall, and that's how they actually detect the motion. But on the right side, most of the dots are on the horizon. So actually, you get to extract more features from the horizon and then estimate your yaw angle based on those extracted features. So really what I want to say here is that optical flow estimates the yaw angle mainly based on the texture or edge of the wall pattern in the camera rendering. But optical flow estimates yaw angles mainly from the horizon if you render with the compound eye structure. And this was very exciting for us because it actually agrees with previous research finding in biology, because it's known that moth gets most information from UV lights and also the horizon features. So they don't actually get a lot of features from other surrounding objects, but they mainly get information from the horizon. So to finalize with the result, this is the result of the yaw angle estimation. So the lower row is the ground truth of your angle. So it's moving from 0, 5 degrees, 10 degrees, 15, 20, 25. And the upper row is the estimated yaw angle. And as you can see, what we want is we want the first row and the second row to be the same. But as you can see, the camera heading angle has more yaw estimation angle than the compound rays. So we were able to actually see that both eyes are better at doing yaw estimation with less number of pixels as well. So as a next step, what we are trying to do now is to do more experiments with other motions with higher degrees of freedom. And also, we want to try different kind of scenes to better understand how this compound eye structure can help the perception. And second, actually, what we simulated is not superposition eye, but apposition eye. So apposition eye is for daytime insect. Superposition eye is for nocturnal insects. And the difference is right here. On the left-hand side, each ray goes to each lens. So that works for daytime insect. But for nocturnal insects, because you don't have enough lights, you want to get one light information with multiple lenses. And that's how you might get some blurry images, but you might use actually more signals in dark environment. So our plan is to compare with apposition eyes to understand how this helps in dim light conditions. So they were the 3 projects that I wanted to present, and I wanted to add a couple of really brief summary of other projects going on in my lab in case that might be interest of your research. Another research that is in a similar line is about target tracking with intermittent measurement. And this project is currently funded by Air Force Research Lab in Eglin Air Force Base. What we're currently doing here is to do the target tracking. Just in case you're not familiar, target tracking means we want to estimate and predict the target's dynamics model based on the measurements obtained at every time step. The challenge here is that we don't know the target motion model and we don't know the environment. So here the assumption is that the ground robots are our targets and they are moving through some road network. And there can be some obstacles like some clouds. We might not be able to get measurements all the time. So we actually get intermittent measurements because of the environment. And how can we still be able to track? And how should we actually, where should the aerial vehicle, the agent, should go if they lose the targets from their field of view? What should they do? So the solutions that we have tried is using transformer-based neural network for motion model learning. So we were using transformer to learn the motion model of the ground robots. And then we compute the waypoints with the highest expected information gain like we did before for the agents on the air, in the air. So we are actually merging that transformer-based motion model into the entropy calculation to find the best waypoint for the aerial agents. So I want to share this hardware experiment video with you. So the black lines are the road network, and these 2 boxes are the occlusion, and the blue square is where we are commanding the robot to go, and the red box is where the drone thinks that it is at. So it can actually track well when it keeps track of the position of the robot because it knows where it is. It usually goes to the position of the ground target, and then it can follow it well. But at some point, this drone might lose tracking of this ground robot. and it's happening right now. So the ground robot actually entered to the occlusion region, and the drone actually lost track of the ground robot. And what it has to do is it really needs to use that learned transformer model to predict where they are, and then incorporate it into planner to find the best, the most informative waypoint to find the robot again. So here it was able to find the ground robot again and then keep tracking. So that's another ongoing project. And I also wanted to talk about the water tank that we have at University of Florida. Actually, this morning I visited Professor David Akin's lab. Actually, you guys have bigger tank, but we also have a good tank to test underwater robotics. We have 15 foot tall, 26 feet diameter with 60,000 gallons of water, and we have 7 underwater motion capture cameras from Qualisys. And this video is not meaning anything right now, but I wanted to share because my undergrad researcher, they were able to do it by themselves by diving into the tank and filming the robot and robot filming my undergrad student to each other. So I was thinking that this can be a good test bed for doing a lot of human-robot interaction in underwater. So it's going to be diver and robot interaction. And really what I want to achieve from this facility is I want to make more of robotics people to be interested in underwater robotics. So I'm working on expanding this facility so that people can also get access to this kind of tank. So I'm working with another researcher team at Cornell where they have XR virtual reality testbed with the physical site. So we want to combine those two so that we can run the experiments together. And we also are working on merging this tank into HoloOcean, which is another underwater simulation tool. So if we can merge those three and then make it work together, even though you don't have access to the real robots or underwater environment, we can actually easily collaborate and you can see what's going on inside. And also in Gainesville, where University of Florida is located at, we have a lot of natural springs. So this is actually our underwater robot at the entrance of our underwater cave. So we actually have a spring that has underwater cave inside. So if we can map those environments really well and make a virtual environment in this simulator, it'll be a very interesting test tool for everyone. So that's it for today's talk that I prepared. So to summarize, I'm working on active perception where the perception is very difficult, and I believe this planning can help better perception in this difficult environment. So I looked into underwater object recognition and magnetic-based navigation for long-duration missions, and also insect vision system for dim light condition navigation. So I'll open the floor for questions, and thank you for listening.
Thank you, Jane. Any questions for Professor Shin?
Any reason you cannot integrate magnetic with GPS?
So we are assuming that we are running in GPS-denied navigation. So yeah, for aircraft, GPS can be easily jammed, and underwater, because it's really deep, we usually don't get GPS, so we didn't consider that yet. Yeah.
I was curious a little bit about the entropy formulation that you used for the gradients. Could you just speak a little bit more about that? I know only my own little teeny tiny narrow part of entropy that I play around with, so I'm really curious about how you encode like a gradient.
Yeah, so it's not really the entropy in the meaning of probability theory, but it's more like entropy is representing how the distribution is distributed. So you have highest entropy when you have uniform distribution. So we wanted to connect that with spatial frequency. So if you actually set some region and then compute entropy, it's talking about how much variation that you have within that bounded box. So we wanted to adopt that concept into modeling the spatial frequency for magnetic navigation.
Thank you. Interesting. So you kind of do like a sliding window?
Yeah, for every pixel. Yeah.
So
So for the morph eye, I do notice there's a task, not only navigation, but also putting the mouth into the flower. Do you think that eye will help for a task like that?
Yes. So that's I think that's a different problem because we were looking into more larger scale navigation where you can see the horizon. So for flower, you have to really find the control algorithm of how the moth reacts to the flower location. Maybe it can be olfaction, it can be vision. So I think it should be different approach because now you have to really follow the flower and it's involving the control algorithm with the perception. So I think, yeah, this won't be the best method. Yes.
Is there any advantage to going for to being to the compound eye like vision system over like many pairs of simple eyes? You know, that might be like easier to engineer like multiple cameras, right?
Yeah, so our goal is to actually make an efficient system. So camera has really high resolution. What we want to do is we want to have low resolution, but with larger sensor field of view so that we can get information. We don't need much features, but we want to get those horizon information more efficiently so that we can use that for light vehicles that can fly. Yep. Yes.
The eyeball stuff is really cool. Do you mind going to the slide picture where you have kind of one next to the other sort of images of this sort of thing? So I know how I think a normal camera works, but I guess I'm not super clear on how the image on the right is being kind of created from the compound eye.
I see.
Is each of these things that looks kind of like a super pixel, is that like from one of the little eyeball thingies?
Yes, correct. So here we are using the Blender simulation where we can put multiple lenses and then it gets one ray information and then it's constructing in this plane.
So like one light ray maps to one super pixel, I guess, or is that not correct?
Actually, we can vary the sampling rate of that rays. So we can actually increase the number of rays, but it will take more time to render this image. So we can kind of manipulate there in the simulation.
So it takes a while to render, but like on the back end when you just have the data, is there any computational advantage to doing this versus a real camera?
My thought was, currently my opinion or my thought is I think we have less number of pixels, so it will be less computation on board the robot. So that's our goal for now for design.
Cool. Yeah, that seems kind of like it might be possible. Like the fact that the number of super pixels is going to be way less than the number of camera pixels is like pretty cool. Thank you.
Yeah, thanks.
You know, regarding the compound eyes, about 20 years ago, we looked at the compound eyes, and one of the advantages that they have is that the field of view is much larger.
Yes.
And when the field of view, let's say, if you have first of all, the compound eyes are one sort of cheap way of implementing a spherical eye. Because if you abstract the compound eye, right, you basically, it is as if you have a sphere. And the center of projection is here.
Yeah.
And then you see an object, you basically connect and you make. But this is a theoretical eye.
Yes.
So by putting the low quality cylindrical lenses that are the omatidia, you get the compound eye.
Yes.
But one advantage is, you know, if you have a planar eye, like we have, and you move, you get optical flow. And the optical flow has a structure, like it's on straight lines that pass from one point, which is the direction of heading.
Yes.
But when you have a spherical eye, then let's say if you move up, this is your translation, then the flows are going to be on geodesics. On geodesics, that they go from this point to that point. And you have a focus of expansion because all the vectors are going away from here.
Mhm.
And you have also at the same time a focus of contraction, because all the flows are going to be going to the antidiametric point. So because you have this additional structure,
Yeah.
it becomes more robust to estimate 3D motion
Oh yeah.
or ego motion.
Yes. Yes.
So we have a number of papers on this, which I will send you.
Yeah. Yeah. Please. Yeah. I'm now looking to more
We
high.
also tried for about 4 or 5 years to understand, because when you have the ommatidia, right, here's one ommatidium, here's another ommatidium, another ommatidium. Does that structure facilitate any visual computation?
Mhm.
So we looked at the problem of motion segmentation. In other words, the insect is moving and other things are moving, and you want to detect them. And we thought that because this is like multiple view vision,
Yeah.
we may be able to do something, but we were unable to find a new constraint.
I see.
So instead what we did is we built what we call the Argus eye by taking, somebody had mentioned that before, we took several cameras and we put them on a structure to have some approximation of a compound eye.
I see.
So, and we did many experiments with it. So Argus was the bodyguard of the goddess Hera in the Mount Olympus.
Okay.
And he had 100 eyes on his body.
Oh wow.
And according to the myth, he defeated a whole army of cyclops that were giants with one eye
Oh, yeah.
in the middle of the forehead.
Yeah.
Which demonstrates that the ancient Greeks, they knew about the power of multiple view vision. So if you look at the world from multiple viewpoints at the same time, it gives you a lot of power.
Yeah. Yeah, definitely. I'll be looking into the papers that you send me, and also higher degrees of motion and how that can help.
Right.
Yeah.
Another possibility with multiple view vision is to do what we call the synoptic vision. Like, if you look at the space here, there is light rays. Every line that you consider, there's a light ray traveling.
Yeah.
And so, when you make an image, you only consider the rays that intersect at one point. That's how we make images.
Yeah.
Consider all the rays that come through one point, and then the intersection of those rays with some surface gives you the image. But there are more rays. There's another ray here, another. You miss those ones.
Right.
So if you are able to capture all the rays, that's called the plenoptic function. There are cameras out there in the market today that are trying to approximate the capturing of plenoptic function. But nothing special really has happened. Anyway, very exciting. Let's thank our speaker again. Professor Shin is visiting some professors this afternoon, and later in the afternoon she may be available if one of you is interested in meeting with her. So if you are interested, you should contact Zhao Min, who is here. What's your email?
Xlin
Xlin.
01.
Xlin01
Yep. At
at
UMD.
UMD.
Yep.
And Zhao Min can arrange that meeting. Thank you very much.
Thank you.